So let's quickly go through section 1.2 here. Just a quick summary, which is on solutions to differential equations and initial value problems. So the general form of an nth order ordinary differential equation, remember that that means that you are taking an nth order derivative somewhere in there, right? So on the left-hand side, we have some function of x and y prime and y double prime all the way up through the nth derivative of y, right? And then on the right-hand side, we just have that it's equal to 0. Okay. Now, every nth order ordinary differential equation can be put in this form. Yeah, everything can be put in this form. You might see them in alternate forms, but this is what we're calling the general form because everything can be put in this form. So oftentimes, we can actually isolate the nth derivative of y on one side of the equation, and so we can kind of solve for it in terms of the other derivatives and x and y itself, right? So then we could rewrite this in such a scenario as the nth derivative of y is equal to some function of x and y prime all the way up through the n minus first derivative of y, right? And that's usually a very nice way to write things, okay? So I'm going to call this equation 1 in red here and equation 2 in blue here. A function phi of x that when substituted for y in 1 or 2 satisfies the equation for all x in some interval I, right? So you have to imagine here that I'm plugging in that y is equal to phi of x. So then y prime would be phi prime of x, y double prime would be phi double prime of x, and so on and so forth, right? All the way up through the nth derivative of y would be the nth derivative of phi, okay? So when I plug that in, if I get a true statement, right? If I get something that satisfies this equation, right? Then that's called an explicit solution to the equation on I. We would call phi an explicit solution. Okay. So as a quick example here, let's show that phi1 of x, which I'm going to define to be sine of x, and phi2 of x, which I'm going to call cosine of x. I'm going to show that both of these are explicit solutions to this differential equation right here, y double prime plus y is equal to 0, and that they're solutions on all real numbers, negative infinity to positive infinity. Okay. So let's just try plugging in phi1, right, and see what happens. Let y be equal to phi1, right? So that's sine of x, right? And then we have to find out what y prime is. We already know that y is equal to phi1, which is sine of x. So then y prime will be the derivative of sine, which is cosine. Y double prime is negative sine, right? So just taking derivatives is all we're doing there to find out y prime and y double prime. Okay, now we're ready to plug things into our differential equation over here, right? Y double prime is negative sine of x, y is sine of x. So you can see where I plug them in over here. Y double prime plus y equals negative sine of x plus sine of x. Of course, that's going to be equal to 0 for all x and negative infinity to infinity. But that's exactly what our differential equation says, right? Y double prime plus y should be equal to 0, right? So it's satisfied. And so then we'll say that phi1 is an explicit solution because we plugged it in and it worked. Okay. Now let's try phi2, right? Phi2 is cosine of x, so y is going to be cosine of x. Y prime is negative sine, y double prime is negative cosine. We plug it into the differential equation, so we get negative cosine plus cosine, again, cancels off, gives us 0 for all x and negative infinity to infinity. So then phi2 also satisfies the differential equation, therefore phi2 is also an explicit solution. Okay. It will not always be possible for us to get an explicit solution to a differential equation. In fact, it won't even be possible for us to always get a solution to a differential equation. But assuming that we can't find an explicit solution, sometimes we can still find an implicit solution. So what is an implicit solution? Well, it's an equation like this, some function of x and y, right, equal to 0, let's say. So every implicit equation can be put in this form, basically, right? And for it to be an implicit solution to the differential equation, when we implicitly differentiate this, it should be equivalent to the ordinary differential equation, okay? So let's try it out with an example, because that's kind of a hard thing to wrap your head around, I'm sure. So let's show that y squared minus x cubed plus 8 equal to 0, right? So this is, I'm going to show that this is an implicit solution to this nonlinear ODE over here. The fact that it's nonlinear doesn't really matter, right? Except that most linear ODEs can have explicit solutions, but don't worry about that, right? And so we're going to show that it implicitly defines a solution to this nonlinear ODE on 2 to infinity. Okay. And so just as a quick note over here, like, why is it only on 2 to infinity? Why isn't it on negative infinity to positive infinity? Certainly, if you look at this equation, you can plug in any x value you want. You can plug in any y value you want, right? Okay. So here's why. The easiest way to see this is let's just try solving for y in this equation, right? So we'll isolate it on one side of the equation. We get y squared equals x cubed minus 8. Now we take the square root on both sides, right? And then now here's where I'm going to stop on this, right? The square root of x cubed minus 8, right? We need this to be defined. We need it to be a real number. So that means that we need x cubed minus 8 to be greater than or equal to 0 in order for us to take the square root of it. So that means that x has to be greater than or equal to 2, okay? All right, so we're almost there then, right? We said that this is the open interval from 2 to infinity, right? So why is x equals 2 not part of this, right? So if x were equal to 2, right, we could plug it into here, right? 2 cubed is 8, minus 8 is 0, square root of 0 is 0, so that would mean that y needs to be equal to 0, okay? If x is equal to 2, that implies that y was equal to 0. However, remember our differential equation is dy dx equals 3x squared over 2y. So if y were equal to 0, we'd be dividing by 0 here, which is really bad, right? And so we have to exclude x equals 2, right? Okay, so that means that x has to be strictly bigger than 2. And so that's why we're restricted to the interval from 2 to infinity. Okay, so that was just a quick note on that. Now let's prove that this is actually a solution, right? An implicit solution to the differential equation. So we have to remember how to do implicit differentiation. Remember that y here is a function of x, right? So I'm going to take the derivative with respect to x on both sides of the equation, right? And when I do that, right, well, then we have a chain rule here. Remember, y is a function of x, right? So that's like an inside function, and it's being squared. So we have to do the power rule first, take the derivative of the outside, right? So we get 2y. And then we have to multiply that by the derivative of the inside function. Well, the derivative of y, well, we have a notation for that. It's just dy dx. So then 2 times y times dy dx. Okay, minus 3x squared, that one's easy, plus derivative of a constant is 0, right? And then on the right-hand side, derivative of 0 is also 0. Okay, so we have 2y dy dx minus 3x squared plus 0 is equal to 0. Okay, now, right, I'm just going to add 3x squared to both sides of the equation. I'm going to divide by 2y, and there we have it. We get the same ordinary differential equation, right? So it's equivalent. When we took the implicit derivative on both sides of the equation, we got a differential equation that was equivalent to the ordinary differential equation we were looking for. Okay, so then y squared minus x cubed plus 8 equals 0 is an implicit solution. Okay, so let's try this one then. Let's verify for every constant c that 4x squared minus y squared equals c is a solution to this differential equation right here. Okay, so for every single constant c, which would mean that this is infinitely many solutions, right? So we're just going to take the derivative with respect to x on both sides of this implicit equation here, right? Do our implicit derivative. So we're going to get 8x minus 2y dy dx is equal to 0. Okay. And then now we're going to try to make it look like our differential equation over here by factoring out negative 2. Right? And if we do that, we get this. If we divide by negative 2 on both sides, well, 0 divided by negative 2 is just 0. Right? So then we get y dy dx minus 4x is equal to 0. Okay. Well, there we have it, right? So thus 4x squared minus y squared equals c is an implicit solution, right? For every single constant c, right? As long as 4x squared minus c is greater than or equal to 0. Why did I write that, right? Well, the reason I wrote that is because if you do the same trick as we did above, right? If you solve for y squared over there and take the square root on the both sides, right? We get that 4x squared minus c needs to be greater than or equal to 0. Yeah. And so that means that x has to be in this interval in order for it to work. Okay. Okay, now I'm going to remark something here. In fact, every ordinary differential equation will either have 0 solutions, right, if it's unsolvable, or if there are no solutions, right, if you can prove that there are no solutions, right? And in the case that it has at least one solution, then it actually has infinitely many solutions because you will always get an arbitrary constant, right? Just like when you take the antiderivative of a function back in Calc 1, right, or Calc 2 even, right, you always pick up an arbitrary constant. So really you have infinitely many different antiderivatives, right? Same thing here with infinitely many solutions in ordinary differential equations. Okay. Okay. So now let's talk about initial value problems. So an initial value problem, right, is a differential equation with extra conditions that need to be satisfied. Okay. So by by an nth order initial value problem, we mean that we're trying to solve an nth order ordinary differential equation like equation 1 or equation 2, right? Subject to these n initial conditions of the form. Well, so we have some initial x value. We plug it into the function and we get a y value. So we get y of x0 equals, let's say, y0. Now we got to plug that same x value into y prime and we get a different y value. It could be the same y value, but it doesn't have to be. So we'll call it y1. Okay. And then we have to plug it into the second derivative. So y double prime of x0 will be y2. Y triple prime of x0 will be y3, and so on and so forth. Keep going all the way up to the nth minus 1th derivative of y, plug in x0, and we get yn minus 1. And so that's n different initial conditions then, since we started at 0 and ended at n minus 1. Okay. So just to sort of clarify that a little bit, what does it mean for to be a first order IVP? Well, you have to have a first order differential equation, and then you have to have an initial condition, one initial condition. So you would stop right here at y of x0 equals y0. If you were a second order initial value problem, then you would need a second order differential equation, like so, right? And then you would need two initial conditions, right? And so on and so forth, right? So let's show that phi of x equals sine of x minus cosine of x is a solution to this initial value problem, right? And so we already showed that sine of x was a solution to this differential equation and that cosine of x was a solution to this differential equation earlier, right? But now we're showing that this new function, phi of x, which is sine of x minus cosine of x, this is a solution to this initial value problem. So not only does it need to solve this differential equation, it also needs to satisfy these two initial values here, okay? So let's just do the differential equation first. So let y be equal to sine of x minus cosine of x, and then y prime will be cosine of x plus sine of x, and then y double prime will be negative sine of x plus cosine of x. And we plug in y and y double prime over here, and we see that everything cancels, and we get 0 for all x values. So it solves the differential equation, okay? That's half of the problem, right? Now we need to see that it satisfies these two initial conditions, okay? So y of 0, right? Remember our y function is sine of x minus cosine of x. So y of 0 will be sine of 0 minus cosine of 0. Sine of 0 is 0, cosine of 0 is 1, so we get 0 minus 1 is negative 1, which is exactly what we wanted. Now we'll do y prime of 0. Y prime of 0 would be cosine of 0 plus sine of 0. So we get cosine of 0 plus sine of 0. Cosine of 0 is 1, sine of 0 is 0, 1 plus 0 is 1. Okay. Now, since phi of x is a solution to the ordinary differential equation and satisfies the initial conditions, it is a solution to the initial value problem. Okay. All right. So now, before we get on to the next topic, right, we need to discuss a few things from multivariable calculus that you may not have had before. Okay, so we know about continuity of functions of single variables, right? Basically, if you're trying to say that a function f of x is continuous at x0, right, then x0 needs to be in the domain of f. So then f of x0 has to exist, basically. And the limit has to exist. So the limit as x goes to x0 of f of x has to exist and has to be equal to f of x0. And fortunately, it's pretty much the same definition for multivariable calculus, right? So we say that f of xy is continuous at x0, y0 if, 1, f of x0, y0 is defined, right? So we can plug in x0, y0 into the function, right? And 2, the limit as xy approaches x0, y0 of f of xy exists and is equal to f of x0, y0, right? So, like I said, this is essentially the same definition as in Calc 1, right? However, it's pretty much trivial to check this limit as x goes to x0 of f of x exists back in Calc 1, right? You just check the limit from the left, and then you check the limit from the right, and you make sure that you get the same number, and then the limit exists, right? With functions of multiple variables, though, it gets a lot trickier, right? So here is just 3 different ways that x and y can approach 1, 2. Okay, so our path P1 over here, the red path, is we're kind of approaching from the left, right? So here we have y is always 2, and then x is slowly increasing to 1, right? Our blue path over here, P2, right? Here we have our x value is always 1, but now our y value is increasing to 2. And then our path P3 over here is just spiraling inward. So your X and your Y are changing at just kind of spiraling inward like that, right? And so that's just a completely crazy path. But we can draw as many completely crazy paths as we want, right? So there are really just infinitely many really crazy ways that X and Y could be approaching 1 and 2. Okay. And so because of that, right, we're going to have to make a great simplification here. Okay. So to greatly simplify matters, I'm only going to give you functions that are continuous on the interior of their domains. Okay. Yeah, so as long as you can show that the point is in the interior of the domain, not on the boundary, then you can say that it's continuous there. Now, in red, I have this really harsh note here that this is not true in general. Yeah, it's definitely not true in general. It's not even true for single variable functions. Like here's a function f of x right here, which is defined for all real numbers. It's defined on negative infinity to positive infinity, right? But it's discontinuous at 0 since the limit from the left is 0 and the limit from the right is 1, right? So it's not even true for single variable functions, okay? But my contract with you is that I'm not going to give you those functions. I'm only going to give you functions that are continuous at x0, y0, or sorry, that if you know that x0, y0 is in the interior of the domain, right? Not a boundary point, right? If it's in the interior of the domain, then, right, you can say that f of xy is continuous at x0, y0. Okay, so that is a great simplification. Okay. Here's another topic for us from multivariable calculus, partial derivatives, which I mentioned in section 1.1. Partial derivatives have exactly the same rules as ordinary derivatives, so they're not that tricky. So, for example, suppose f of xy equals x squared plus y cubed minus 3xy. Okay, we write partial derivative of f with respect to x, right? That's one way that we could write the partial derivative. Here's another way we could write the partial derivative, this f sub x notation, right? And so one of these is the Leibniz notation, one of these is the Newton notation, and I will use them both. Yeah. Um, so so let's say we're taking the derivative of this thing with respect to x. Now, x and y, those are two independent variables. As x changes, y is not changing. As y changes, x is not changing. Yeah. So when we write partial derivative of f with respect to x, right, remember that's a rate of change. We're asking how much does the functional value f change as x changes only, right? Fair enough. So only x is changing here, right? And another way to say that is, well, if y is not changing, then y is a constant. Yeah. So we're going to treat y like it's a constant if we're taking the derivative with respect to x. So let me show you here. So the partial derivative of f with respect to x, right? Well, f is x squared plus y cubed minus 3xy. So then the partial derivative of f with respect to x is just the partial derivative with respect to x of this function, x squared plus y cubed minus 3xy. Now I'm going to use the sum and difference rule because remember all the rules are the same, right? So I can distribute that to this term, I can distribute it to this term, I can distribute it to this term. So I'm taking the partial derivative with respect to x of x squared plus the partial derivative with respect to x of y cubed minus the partial derivative with respect to x of 3xy. Okay. Now this first derivative over here, right? This is just power rule, right? And it's like the derivative just is only a function of x, right? So we're just going to get 2x. Okay. Now the second derivative over here, we're not doing implicit differentiation anymore. Remember that x and y are independent variables here, okay? Yeah, so we're not saying that y is a function of x here, okay? So then the derivative with respect to x of y cubed, well, y cubed is a constant. It's not changing as x changes. So then the derivative will be 0, okay? And then minus the partial derivative with respect to x of 3xy. Well, 3 is a constant, y is a constant, and we're multiplying them by x, so those are constant multiples. We can pull them out of the derivative. So we get this is the same thing as minus 3y partial derivative with respect to x of just x. Okay. Okay. So then now we can simplify this. We just get 2x and then minus 3y. The derivative with respect to x of x is just 1, so we just get minus 3y there. Okay. Now, similarly, we could ask for the partial derivative of f with respect to y. Okay, so then we just do the same game here. We distribute this derivative to each one of these terms, right? Now your x is a constant, right? As y changes, x does not have to change. Okay, so then the derivative of x squared is just 0, right? The derivative of y cubed is 3y squared, right? We pull out our constant multiple, which is 3x here, right? The derivative of y is just 1, so then we get 3y squared minus 3x. All right, so that's pretty much all we need to know for multivariable calculus at the moment. I may mention some other things later. All right, why do we care about all that though? Picard's theorem or Picard-Lindelof theorem or the existence and uniqueness theorem is what I'll usually call it, EUT for short, existence and uniqueness theorem. So basically, we want to solve initial value problems in this class, but sometimes we don't know if we can find a solution or not. Okay, so the existence and uniqueness theorem is one way that we could say that there exists a solution to this initial value problem, right? And not only that, but that solution is unique. So this is the only solution to the initial value problem. right? So you'll recall that I said that every differential equation has infinitely many solutions, but initial value problems, right, they can have exactly one solution. Yeah, because they have to satisfy those initial conditions. So then the arbitrary constants are no longer arbitrary at that point. Yeah. And so the existence uniqueness theorem gives us conditions under which we can say that this first order derivative, right, has a unique, this first order IVP has a unique solution. So here's how it works. Let's consider the IVP dy dx equals f of xy. So it's a first order ODE with one initial condition, right? So if f of xy and the partial derivative of f with respect to y of xy are continuous in some open rectangle, right? So what is an open rectangle? Well, it's a rectangle, right? Where the x values between a and b and the y values between c and d, right? For some numbers a, b, c, and d, basically. That's all a rectangle is, right? And so it's an open rectangle because we don't allow x to be equal to a, right? We don't allow x to be equal to b. We don't allow y to be equal to c. We don't allow y to be equal to d. And that's what makes it open, right? Just like an open interval. So this is an open rectangle, okay? So for some, if f and f sub y here, if f and the partial derivative of f with respect to y are continuous in some open rectangle containing your initial value, right? So remember, here's your initial value over here. Y of x0 equals y0. That has an x coordinate and it has a y coordinate. So that's a point in the xy plane, right? So if your function f and the derivative of f with respect to y are continuous in this open rectangle, right, then there exists a unique solution, phi of x, to the initial value problem on an interval x0 minus delta, x0 plus delta for some positive delta. This is basically just saying that there is some interval on which there exists a solution to the initial value problem, right? And that interval contains x0. That's all that's saying. Okay. So let's see if we can apply this. Okay. So does the existence of uniqueness theorem imply a unique solution to the initial value problem? Well, here's an initial value problem right here, okay? So then my f of xy is this function right here, y squared minus x squared to the 3/2 power. That's my function f of xy, right? Here's my initial value. That's my x0, that's my y0. So let's just write a few things down. X0, Y0 will be 0, 1, right? So that's the point that the open rectangle has to contain, right? F of xy is equal to y squared minus x squared to the 3/2 power. And then now we need to take the derivative of that with respect to y, right? And so we've had some practice with that now, right? We know how to take derivatives. It's just like in Calc 1, but now we're treating x like a constant, right? So we're going to get derivative of the outside will be 3/2 y squared minus x squared to the 1/2 power. But because of chain rule, we need to multiply by the derivative of the inside, which will just be 2y. Okay. And now we simplify, we get 3y square root of y squared minus x squared. So the domain of f of xy, right? Let's see if we could find that, right? Why are we interested in a domain? Well, you'll recall that finding whether a function is continuous at a point is really hard for multivariable functions. And so my contract with you was that I would only give you functions where if the point is in the interior of the domain and not on the boundary, then that function is continuous at that point, right? So since y squared minus x squared is raised to the 3/2 power, right? That's like cubing it and then taking the square root. So since we're taking the square root of y squared minus x squared, that means we need y squared minus x squared to be greater than or equal to 0. That's the same thing as saying that y squared is greater than or equal to x squared, which is the same thing as saying that the absolute value of y has to be greater than the absolute value of x. Now, I just want to make a quick note here. It's an algebra note that the square root of y squared is not y, it's the absolute value of y. Okay, y might not be positive, right? So we need to take the absolute value of it. The square root will never give you a negative number. So this is absolutely important. The square root of y squared is absolute value of y, and the square root of x squared is absolute value of x. So then when we simplify this expression, when we take the square root on both sides, we get the absolute value of y is greater than or equal to the absolute value of x, which looks really nasty. Okay, but let's see what we can do about that. The boundary of the domain, right, will be when the absolute value of y is equal to absolute value of x. Okay, that will be the boundary of the domain. Okay, so then if absolute value of y is equal to the absolute value of x, then that means that either y is equal to x or y is equal to negative x. So let's draw a picture of the domain then, right? So you can see in solid blue lines over here that I've drawn y equals x and y equals negative x. Okay. All right, so the reason I drew them as solid lines is because they are part of the domain, right? We're allowing for absolute value of y to be greater than or equal to the absolute value of x. So this will be part of the domain, okay? So I drew them as solid lines. Now, right, how come I shaded these regions right over here? Well, I basically just plugged in points to see whether they were in the domain. So for example, if I plug in the point 1 comma 0 that lies on the x-axis over here, right? Well, then if I try to plug it back into my equation over here, right, this equation, I try to plug it back into this one. Oh, okay. I don't think it would still let me. Draw. All right. Well, anyway, if it's not going to let me, then it's not going to let me. So if I try to plug it back in here, x equals 1, y equals 0, then we get 0 is greater than or equal to 1. That's false, right? So then this point, 1, 0, is not in the domain. Okay, so that means that this entire region right here, this triangular region, is not in the domain, right? It's like a test point. Okay, now I do the same thing in each of these regions, right? And I see that this part is in a domain because if we plug in 0 and 1, well, x equals 0, y equals 1 is greater than or equal to 0. It satisfies that. So then this is shaded in. So everything in this region is in a domain, right? If I plug in -1, 0, I get 0 is greater than or equal to 1 again, which is false. Right? If I plug in 0, -1, then I get 1 is greater than or equal to 0, which is true. So there we have it. Okay. So there's a nice picture of the domain of f of x, y. Now let's remember what my initial value was, right? 0, 1 was my initial value. And so we see that that rests firmly in the interior of the domain. It is not on the boundary, right? And so because it's an interior point, right, my contract with you is that f of xy will be continuous at 0, 1 then, okay? So f of xy is continuous at 0, 1. Going back to my conditions of the Picard-Lindelof theorem or the existence of uniqueness theorem, I've shown that f of xy is continuous at x0, y0, basically. Okay, I still have to show that the partial derivative of f with respect to y is continuous there, though, right? So I'm not done yet. Okay, so on to that part. Now let's look at the domain of f sub y. Now, we're going to take the derivative of f with respect to y, right? We got 3y square root of x squared, y squared minus x squared, right? And it has exactly the same domain as f of xy because we're still taking the square root of y squared minus x squared. I mean, yeah, we're multiplying by 3y over here, but I mean, we can plug in any y value we want. It's not going to matter, right? Well, what makes this a real number is if the square root of y squared minus x squared is a real number, okay? So, in this particular scenario, we have that this has exactly the same domain as f of xy. This will not always happen, okay? In any case, though, right, since it has the same domain, right, that means that f sub y is also continuous at 0, 1. So we've shown that f is continuous. We've shown that f sub y is continuous, both at 0, 1. So then the existence uniqueness theorem applies, and it follows that the initial value problem has a unique solution, okay? Now let's try it again with this one, right? Does the existence uniqueness theorem imply that there is a unique solution to the initial value problem? Right, so we have dy dx is the square root of 4 minus x squared minus y squared, and y of 2 is equal to 0. So I have my function f. I have f sub y. Here's the derivative of that simplified. Okay, and then x0, y0 will be 2, 0. Let's look at the domain of f of xy. I gotta wait for this thing to load first. Why that's waiting to load there, right? We need for 4 minus x squared minus y squared to be greater than or equal to 0, right? So because of that, right, that means that x squared plus y squared has to be less than or equal to 4, okay? So then the boundary of the domain would be x squared plus y squared equal to 4, okay? But this is the equation of a circle of radius 2 that's centered at the origin, right? So here I've drawn a circle of radius 2, and I've drawn it as a solid line rather than a dashed line. The reason I drew it as a solid line is because we're allowing for x squared plus y squared to be equal to 4. So this boundary is part of the conditions of being in the domain, okay? Now, right, our initial value, well, okay, I guess we have to plug in points to see whether the inside of the circle is in the domain or the outside of the circle is in the domain, right? If I were to plug in 0, 0, right, into this condition right over here, I get 0 squared plus 0 squared is less than or equal to 4. That's absolutely true. So then because 0, 0 is in the domain, the entire interior of the boundary is in the domain over here, okay? Or the entire interior of the circle is inside the boundary. Now, our initial condition was 2, 0, right? Okay, and that lies on the boundary of the domain of f of xy. And so, because it lies on the boundary, that means the function is not continuous there. And the reason it's not continuous there is because we can't draw an open rectangle around it. Any open rectangle that we draw will contain points that are not in the domain, right? And so there we have it. So f of xy is not continuous at 2, 0. In order to apply the existence and uniqueness theorem, we need for both f and f sub y to be continuous at 2, 0. And I just showed that f is not continuous at 2, 0. So we cannot apply the existence and uniqueness theorem. Or another way to say that is that the existence and uniqueness theorem does not imply that there is a unique solution to the IVP. Here's an incorrect way to say that. If you said that the existence and uniqueness theorem implies that there is not a unique solution, then that is absolutely false, right? That is not what the existence and uniqueness theorem says. The existence and uniqueness theorem will only tell you that there is a solution. It'll never tell you that there is not a solution, though. Okay, fair enough. So either the existence and uniqueness theorem applies, and you can say that there is a unique solution, or the existence and uniqueness theorem fails and you can't apply it. That's the most that you can say, though. Okay. All right, so that's it for section 1.2.